Hi, good day, everyone. Welcome back to the start of the second afternoon of SGT Online 2021. And our first session this afternoon is about sign graphs. We'll have a second session about eigenvalue location and applications, or the distribution of eigenvalues. And as yesterday, the link to the next session will appear close to the end of the session, and then you can easily move to the next session. And it is my pleasure to now introduce the organizers of this session about sign graphs. So Professor Francesco Belardo from the University of Naples, who kindly accepted our invitation to be here and help us organize this session. And Professor Vilmar Trevisan from Porto Alegre, who is the leader of one of the research groups that is organizing this event. So, welcome.
Good day, everyone.
Okay. Good afternoon, or good night, or maybe good morning for someone. Let me tell you a bit about this session. You know, when we were trying to organize this session, you know, from our group, actually from, I think from Cibele Vinagre, one of our team members, she thinks it was a good idea to talk about sign graphs. It was fortunate that I had, you know, I was attending this year in Naples, and Francesco Belardo was there, that I consider one of the experts in sign graphs, and he helped me organizing. So he's going to be one of the speakers, but I asked Francesco to tell about the other two people, please.
Yeah, you see, this event is dedicated, in fact, to young researchers. So I will speak about basic concepts, but then the other speaker will speak about some more detailed arguments about sign graphs. Shall we introduce them later, right? This is my time. I can speak about my topic, correct?
Yeah, but I want to just put the people up, and you know, just to anticipate before your talk, Francesco, that Maurizio Brunetti also is going to be
Maurizio
our
Brunetti.
second. He's also from University of Naples, and Zoran Stanic from Serbia, the University of Belgrade. So it's I consider the three of them some of the leading experts in sign graphs. So I thank all of you for this. I thank Francesco to help organizing. And just one word, as Francesco said, you know, the idea is exactly because we want to learn more about, you know, our group wanted to learn more about sign graphs, and it's not actually intended for a research-oriented, at least not in principle. So that's why some of the talks, and especially Francesco's talk, is going to be about basic concepts. So anyway, it's my pleasure to introduce Francesco Belardo, my good friend and researcher from University of Naples. And as I said, he's one of the experts in sign graphs, among other things. So Francesco, it's your talk.
Thank you very much. Okay, I'm an expert. In fact, I started studying sign graphs just recently. In fact, I think in 2012 or 13. Can you see me, right? Because I do not have feedback. Can you see the slides?
Yes, we can see it.
Okay, sure.
It's perfect.
Okay, fine.
Thank you.
So there are other people who are definitely more expert than me. I devoted my attention, in fact, to the spectral sign graphs. There were, when I started already, several interesting papers, but still this topic was not yet well developed. Now, in the recent years, this topic has been more explored, and from sign graphs, we are also this was also generalized to a larger to the context of game graphs, which I will not speak about in this talk. So I will deliver basic concepts. I will try to restrict this discussion on the basic stuff on sign graphs. I will introduce two matrices of sign graphs, but there are also other matrices that one can consider. And then I will mention some important results about the adjacency matrix and the Laplacian matrix of sign graphs. Of course, it's not everything, but it's a good start. I believe this is a good start for people who are interested in the study the spectral sign graphs. So, what is a sign graph? Let's consider the definition. A sign graph is just a graph with a signature on the edges, which means that you have a graph G, a usual graph. It can be even somewhat more complicated than the usual graph. And on each edge, get a value +1 or -1. And these values are called the signature of the graph. In general, the graph, as called the underlying graph, because the sign graph is the pair by the graph and the signature, has no restriction. And in this context, I will just consider that the underlying graph is a simple one. But in general, you can, or in some situation, it may be useful to have parallel, multiple edges, loops, and so on. What is relevant in this theory is the sign of the cycles. This will be clear later. And if you have a cycle in your graph, the sign of the cycle is the product of its edge signs. So here we have an example of a sign graph. The advantage of sign graphs is that you can depict them easily, and you can use, for example, positive edge to be denoted by bold lines, and to have dotted lines for negative edges. Let's continue. Well, when these sign graphs, in fact, appeared in the literature, were first defined by Harari in 1953, I think, to deal with problems in social psychology. But they somehow appeared already in the literature and in other topics, somewhat in some other area of mathematics. But it was Harari who first gave the best, let's say, best definition, because he considered the sign of cycles, which is a fundamental concept in this theory. Now you can find sign graphs in physics, in computer science. I will mention the resolution of the sensitivity conjecture thanks to the spectral sign graphs, in biology, in economics, and so on. So you can find sign graphs in various contexts. But the guy who has worked most on sign graphs is Tom Zaslavsky, and he had a paper in 1982, very important, and now he's also running two dynamic surveys about notation and bibliography on sign graphs. So he developed this theory and the theory of game graphs after this, the theory of sign graphs. Okay, let's speak about definitions of sign graphs. Many definitions comes from the theory of the unsigned graphs, let me say. So you have order and size, which is the order and size of the underlying graph. You have the degree, you have the diameter, and so on. But of course, you have the signature. So you have also some other definition which depends on the signature. So we have, for example, as I said, negative and positive cycles, but we can have a negative and positive degrees. We can have a negative and positive, we have in fact negative and positive walks, and so on. And there is a property which is fundamental in this theory, which is the property of being balanced. A sign graph is balanced if and only if all cycles, if any, are positive. And Harari gave this definition of balance, and he characterized also the balance, and he said that he proved, in fact, that a sign graph is balanced if you can divide the vertex set in two clusters, such that you among these clusters you just have the negative edges, and the positive edges remain within each cluster. So I have here an example. So you can see that these negative edges are just the crossing ones, and negative edges appear only within the clusters. Of course, by definition, trees are balanced graphs. Okay. Next, we have also concept of regularity with some graph. The regularity can be given with respect to the usual degree, but also with respect to the positive and negative degree, which is, of course, the positive degree is the number of positive edges incident with the vertex, and negative degree is, you can imagine, is the same, but with the negative edges. What is interesting is that the definition of a net regular signal graph, when it is constant, the difference between positive and negative degrees, and you have a co-regularity when your sign graph is at the same time regular as the underlying graph, and net regular with respect to the signature. I should have here a net regular sign graph. This graph is net regular, but it is not, of course, regular. Another critical concept, fundamental concept in sign graphs is the signature switching. Well, you fix a set of vertices, you consider the complement and the setting, the edges crossing this between these two sets. If you reverse the edge sign in the cut, this is called the sign switching. Of course, when you change the sign of these edges, you are considering another signature. But this signature is said to be equivalent to the previous one. So we have a concept of switching equivalent signatures, and whichever is the switching you use, no matter what, the sign of the cycles will be preserved. So in general, we speak about switching a switching class of sign graphs when you not only consider the signatures which are equivalent, but also you allow vertices to be permuted. So you combine isomorphism of the underlying graph with the signature switching. In that case, we speak about the switching isomorphism class. So here I have an example of switching. See, we have this sign graph. I take these three vertices, and then I switch the sign of the edges between U and G minus U. And you can see that we have obtained another graph which is equivalent to the first one, and you can notice that the sign of the cycles remains the same. Balance, it's of course important because when you have a balanced graph, then it's switching equivalent to the all positive signature. This means that I can change all signs of the edges by this signature switching to the all positive signature. All edges get +1. Here there is the proof. I do not have time to stay on the proof, but the bottom line is that balanced graphs, in fact, are signed representative of the unsigned graphs. So usual graphs can be seen as balanced graphs in the theory of signed graphs. Okay, let's go quickly to the matrices associated with signed graphs. Of course, we have the adjacency matrix, naturally defined. Edges gets ±1. The entries of the matrix are ±1 when the edge is negative, positive, or negative, respectively. We have a Laplacian matrix, but on the diagonal you get the vertex degrees of the underlying graph. So the definition is almost the same. You can have also other matrices associated to sign graphs. For example, the net Laplacian defined by Zoran Stanic, and even other. But I will not mention them during the remainder of this talk. What is nice, I find it I find interesting that the Seidel theory of graphs, in fact, is embedded in this theory of in the adjacency theory of sign graphs, because when you consider the Seidel matrix is 0, 1, -1 matrix, And this can be seen as the adjacency matrix of a signed complete graph. Okay, let's have a look to the adjacency matrix of some example of a signed graph. So you can see the matrix is real symmetric, so the eigenvalues are real numbers, so you can order them. Unfortunately, this is now not anymore a non-negative matrix, so we lose, for example, the Perron-Frobenius theory. Or let me say, we don't lose it completely, because balanced graphs will, in some sense, take the advantage of that theorem. When you consider the Laplacian, on the same example, you can see, well, this matrix is symmetric, diagonally dominant, and so on. The entries on the main diagonal are the degrees, so they are positive, non-negative. So these eigenvalues are real numbers, and they are greater than or equal to 0. Next, well, natural question is, what happens when I consider two graphs from the same, two signed graphs from the same switching class? What I expect is that, of course, they have the same eigenvalues, in fact. And switching can be seen in terms of a switching matrix, and then you can see that the adjacency matrix and the Laplacian matrix of two switching equivalent graphs are switching similar. So that means that they are similar matrices by means of a switching matrix. If we consider, okay, of course, eigenvalues do not change when you apply switching, but eigenvectors do change. In fact, the entries related to switched vertices are switched in sign. So eigenvector components do change just in sign. And when you speak about switching isomorphism, you can combine the permutation matrix with the switching matrix, and then have the matrix called signed, sometimes called signed permutation. So if gamma and gamma prime are switching isomorphic, then it means that the adjacency matrix or the Laplacian matrix are similar by means of a signed permutation. Of course, recall that the signs of cycle is what is important in this theory. Okay, now let's focus our attention to the adjacency matrix of sign graph, or sign graphs. Here there are some results that I would like to mention to the audience. First of all, you have the coefficient theorem or the Sachs formula, spectral moments, the Acharya spectral criteria of balance, interlacing theorem, and symmetric spectrum. I will discuss these results on sign graphs. I keep in mind that the largest eigenvalue and the spectral ratio are, of course, important in this theory, but they will be considered by Maurizio in the next talk. So one important result in this theory is the Sachs formula. Of course, this can be seen as a bridge between the combinatorial structure of the sign graph and the linear algebra with the eigenvalues. So this theorem is very important. In fact, the proof is the same as the old one. You have to just to consider the sign of the cycles. And from this formula, one can also observe that it's the sign of the cycles which may change the entries of these coefficients. Another important aspect is considering the powers of the adjacency matrix. For unsigned graphs, it is well known that the powers count the number of walks between two vertices, but in the signed graphs, we have the same results, but in the signed variant. And when you consider the powers of the matrix, you in fact have to consider the difference between positive and negative walks between two vertices. And of course, if you consider the trace of this matrix and you have then the spectral moments, then you have that you have this relation, which is a relation between, in fact, the powers, some of the powers of the eigenvalue, and the difference between closed blocks, positive closed blocks, negative closed blocks of a given length in the sine graph. Okay, another results, this is by Acharya. He was a pioneer, in fact, of spectral sine graphs. These results is from 1980, and Acharya proved that for a sine graph, you can understand from its eigenvalues that it is balanced when these eigenvalues are the same as a multiset to the eigenvalues of the underlying graph. So a graph is balanced if and only if the spectrum is the same as the spectrum of the underlying graph. Now, this result is, of course, has been generalized recently to gain graphs, and there is also another variant which just looks to the largest, to the spectral radius, and you can recognize the graphs to be balanced when just the largest eigenvalue is equal to, let me say, the spectral radius of the underlying graph. And this result is very interesting because I'm not sure about the proof of Stanic, but when you prove this for gain graphs and still holds for gain graphs, the eigenvector, the principal eigenvector entries related to the largest eigenvalue gives you the partitions in the Harari sense for the balance. If you have the structure of gain graphs, these will give you even the potential function. But this is a concept I will not discuss here. And I would observe that in general, of course, you have this inequality. So if you get the equality, the graph is balanced, but if it is not balanced, this inequality is strict. Okay, we have also an interlacing theorem. The interlacing theorem holds for symmetric real matrices. It holds for complex Hermitian matrices. In fact, it holds also for more general situation. And for sine graphs, it naturally holds. And then you have that the eigenvalues of the vertex deleted subgraphs are interlaced by those of the parent signed graph. And another feature that it's, unfortunately, this does not go well, let me say, to sine graphs, is the concept of symmetric spectrum. Everyone who deals with the spectral graph theory knows that for the adjacency spectrum, you have that the spectrum is symmetric with respect to the origin if and only if the graph is bipartite. And of course, there is also another result which is related, based on pair of bands, which you can obtain the same by looking to the least eigenvalue in case of connected graphs. Well, the question is whether these results can be stated for sine graphs. Well, the answer is negative, but we have somehow some generalization because we have we speak about sine symmetric graph when the sine graph is switching isomorphic to its negation, which means that you consider the same underlying graph and you reverse the sign of all edges. And if these two graphs are isomorphic, switching isomorphic, then you say that the graph is sine symmetric. And bipartite graphs for our signed graphs are sine symmetric. And in general, you get that we have an example of sine symmetric with signed graph. And then we get in general that if the signed graph is sine symmetric, then the adjacency spectrum is symmetric with respect to the origin, because you have, of course, that this A and minus R are similar, and then the eigenvalues must be symmetric with respect to the origin. Now, Unfortunately, no, not unfortunately, this theory has some exceptions. I mean, I would say that, in fact, there are graphs which have symmetric spectrum, but they are not sign-symmetric. And I found an example on the Sider theory, and I posed the question whether there are even more sign-symmetric, not sign-symmetric sign graphs with symmetric spectrum, and this was considered by several scholars. Let me mention Gorbani, Hemers, Ramezzani, and some other. And for example, they provided this infinite family, among others, of non-sign symmetric graph with symmetric spectrum. Here you can have any number of vertices, and this graph will never be sign symmetric. Okay, now we switch to the Laplacian matrix. I think I have to speed up a bit. I will just mention a few results about the Laplacian. When you define the Laplacian matrix, it's important to understand which is the incidence matrix. Then we have a signed matrix theorem, and the least eigenvalues is connected to balance. I will just skip these last two things. Incidence matrix of signed graphs can be easily defined in this way. When you have a positive edges, you can consider these oriented edges. So for each edge, you consider two arrows. So that's why we have bidirected graphs. And if the edge is positive, then you must have this kind of oriented edge. When you have negative edges, you must have this, let's say, unoriented, because these arrows are not concurrent. And let's say that, in fact, the trick is that the product of these signs must be the negation of the signature of the sign of the edge. This also is good in general when you consider not only sign graphs, but also gain graphs. And you can see that from a signed graph, you can have several bidirected graphs. This concept, in some sense, is the same as for the Laplacian of unsigned graphs. Of course, from this step, you can have several bidirected graphs, but when you go back, you just built just one single signed graph. And if you use the entries of this incidence matrix, is what you expect is that you can build the Laplacian matrix of the graph. And here is the formula we need. So if you make B transpose, you get the Laplacian of the signed graph. Of course, it doesn't matter which is the B orientation you have decided earlier. Let me mention this signed matrix theorem, very important in this theory, because similar to the Sachs formula, provides a connection between the combinatorial structure of the sign graph and the eigenvalues. And this is very similar to the one stated for the signless Laplacian or unsigned graphs, but instead of odd unicyclic graphs, you have here unbalanced unicyclic graphs. So if you compare these two theorems, are almost the same. And notice that when the least coefficient is 0, then whenever gamma has no negative cycles. From the Laplacian, you can deduce whether the graph has balanced components or not. This result is from Zaslavsky. And in general, when the least eigenvalue is non-zero, then the signed graph has no balanced components. And then you can introduce a concept of frustration. This is known in the literature as frustration, which is the number of vertices or edges you need to remove to delete in your sign graphs in order to obtain a balanced graph. And if you related to vertices, this is called the frustration number. Related to the edges, this is called frustration index. And especially the frustration index is relevant in applications. Well, we have these results. I proved this result in 2014, but I'm not sure whether I was the first proving this. The least eigenvalue of the sine of the Laplacian is a lower bound for the frustration number than the frustration index of the graph. And in fact, I was more interested in evaluating this equality. And later we had these results from Martin in 2017, which he gave bounds for the frustration index in terms of the least Laplacian eigenvalue. So for this reason, it's natural to call this least Laplacian eigenvalue as the algebraic frustration. Okay, we have also interlacing theorem in terms of the edges as for the Laplacian of assigned graphs, and we also have the Laplacian spectral moments, which, especially from the third on, you find the signature of the cycles in the formulas. Okay, just to conclude this, I'd like to say that when you consider the Laplacian sine graphs, in some sense, this is a theory which moves from the Laplacian of assigned graphs and the assigneless Laplacian of assigned graphs. So these assigned graphs, the Laplacian theory of sine graphs is in some sense, let me say, bounded by those based on simple graphs. And one last slide, you can see that from the eigenvalues, you can detect this combinatorial information on the graph. From the Laplacian eigenvalues, I think you can retrieve more information. And that's why I believe that the Laplacian theory is somewhat stronger with respect to the Chern-Simons theory, because you get less cospectral non-isomorphic pairs. And with this, I recommend this if you want to start studying this topic, I recommend the papers from Tom Zaslavsky and one paper I published some time ago with Choa, Bakul, and Wang, which is where there is a collection of open problems in the spectral theory of sine graphs. Okay, I think that's enough. I hope that everything was clear for everyone.
Well, thanks, Francesco. Because we are a little bit over the time, if there is any question for Francesco, I'll ask you people to ask at the end, where we're going to have some closing. Well, thanks, Francesco, again. It's now my pleasure to introduce Maurizio Brunetti from the University of Naples also. And Maurizio, it's with you now.
Okay, let me share the screen and I open my file. Do you see my first slide on the screen?
Yes, we do. It's working
okay.
Fine.
So it's obviously I'm proud to be part of this SB Maki event. And Vilma, do you remember? Probably you surely remember the very first time we discussed this event. We were both in Naples, and now, well, it is time to start this middle talk of this session devoted to sine graphs. Well, what we learned just a few minutes ago, Francesco told us that the ingredients to define a sine graph are a graph G and a signature function defined on its edge set. Well, let me assume the non-emptiness and its simplicity, just for sake of brevity, even if it's not strictly necessary. Usually, empty graphs can be regarded as sine graphs which are actually balanced, since they have no negative cycles. And Francesco also recalled how to define the adjacency matrix, which is defined, well, you take the ordinary adjacency matrix OG, and then you replace all the ones with minus ones in entries ij corresponding to negative edges. This is clear that unless no negative edges exist, this is equivalent to require that sigma is not the all positive signature. Well, A of gamma contains some negative entries, and this fact has a striking consequence. We have to say adeus, Senor Perron, adeus, Senor Frobenius. I'm not suggesting with this cinematic slide that Perron and Frobenius were twins, but just that we cannot rely on the beautiful properties ensured by the Perron-Frobenius theorem holding for unreducible non-negative matrices. And just to list some spectral peculiarities, I don't know how to, just a moment, please. Okay, no. Just to list some spectral peculiarities of sign graphs, let me fix some notation. Let gamma be a sign graph with n vertices, and then we index the several eigenvalues in a non-increasing way, so the lambda 1 of gamma is the largest eigenvalue. Well, lambda 1 of gamma is called the index of gamma, and if you consider the maximum among the moduli of the several eigenvalues, you have the so-called A spectral radius of gamma. This is an important point, since in an unsigned context, index and the notion of the index and the spectral radius are interchangeable, and this is a consequence of the Perron-Frobenius theorem. This is not the case in when you deal with sign graphs, since for some sign graphs it can happen that the spectral radius is not equal to the index, and this is definitely the minimal example. If you take any signature on the triangle that makes it unbalanced, and you have just to take an odd number of negative edges, well, the spectrum is given by -2, 1, 1, and you can immediately see that the index is 1 and the spectral radius is 2. You can ask if for some connected graph the index is always simple. This is not true. The index can be non-simple, and again, the same example shows that the index can have multiplicity bigger than 1. In this case, the eigenvalue determining the spectral radius is simple, but this is not always the case, since for some connected sign graphs, the eigenvalue determining rho alpha or gamma could be non-simple. And as an example, let me take the unbalanced quadrangle, the cycle with 4 vertices having an odd number of negative edges. And you see that the multiplicity of the eigenvalue corresponding to the spectral radius, the multiplicity is 2. There is another feature typical of sign graphs that I see this property as a sort of trap. It can happen that in your argument you are tempted to believe that when you add edges, the index and the spectral radius cannot decrease. But this is not the case in a sign graph theoretical context. And the example is given by this pair of graphs. If you start with P4 and then you add a negative edge connecting the pendant vertices, say, you see that both the index and the spectral radius decrease. The index of P4 is twice the cosine of pi over 5, and the index of C4, which is also equal to the index, is square root of 2. As you can see, the lambda 1 of C4 unbalanced is strictly less than the lambda 1 of P4. Now, let me state and prove two propositions, since the aim of this talk is to advertise this the realm of sign graphs. So it is important to know which are the tools used to prove facts. Well, consider now the set of indices of the several sign graph you can define on the same underlying graph G. This set has a maximum, and as Francesco announced, this is also as a consequence of the theorem by Zoran proved in 2019. The maximum of all these indexes is achieved by the balanced graph, by the all positive signature defined on G. How it is proved? Well, if you take a unit eigenvector corresponding to the index of your sign graph, well, by the properties of the Rayleigh quotient, the index is given by the product of transpose of x times a times x. This is a sum of several summands, and surely this number cannot decrease if you replace the several summands with their norms. And always because of the properties of the Rayleigh quotient, this number is less or equal than the index of the all positive G. And that's all. This is the proof of this proposition. A similar result holds for the spectral radius. If you consider all the possible spectral radii of the sign graphs obtained from the same underlying graph, well, the maximal spectral radius is achieved by the all positive signed G, which is also the index of the underlying graph G. Which is a proof. By proposition 1, we know already that the index of your sign graph G sigma is not bigger than the index, say, of G. Then you take a unit eigenvector Y corresponding this time to the least adjacency eigenvalue. And again, by the properties of the Rayleigh quotient, the lambda n is equal to this product here, which is not less than, when you replace each summand with the opposite of their norm, you obtain this first inequality. And by the property of the Rayleigh quotient, you have this second inequality. Now, by definition, say, and by elementary properties of matrix theory, the least Laplacian eigenvalue of the all negative sign G is equal to minus the index of G plus. Now, if you put together these two inequalities, you get the result. The spectral radius of G sigma is the maximum between these two numbers, and then you obtain the equality claimed. These two propositions have a nice corollary. If it is true that both the index and the spectral radius are not bigger than the index of the underlying graph G, all known upper bounds for lambda 1 G are also upper bounds of the index and the spectral radius of your sign graph. It means that if you take your favorite book on bounds, for instance, the nice book written by Zoran on the inequalities for graph eigenvalues, and all the upper bounds you find there for lambda 1 G are also upper bounds for the index and the spectral radius of your sign graph. What about lower bounds? Well, the late David Gregory, in his notes written down in 2012, proved a lower bound involving the average vertex degree. The average vertex degree is obtained by summing all the vertex degree, and then you divide by the order of G. This is equal then to twice the size over the order. Well, he proved that the spectral radius of your sign graph is not less than square root of k, over the square root of the average vertex degree. Well, obviously, because of the propositions that we have proved before, square root of k is also a lower bound for the spectral radius of the unsigned graph, but the proof is different. You have also that the equality holds if and only if G is k-regular, and the square of the matrix of the adjacency matrix is equal to ki. There is a rich theory studying the so-called weighting matrices, matrices satisfying this condition, but we know that for when the order is odd, no weighting matrix exists. But let me stress this fact. There is a classical proof for the unsigned case to prove that the square root of k is a lower bound for this spectral radius, which involves the normalized all-one vector. Well, that proof is not anymore true in this context, but the result is, in any case, holds. Gregory proposed to look at the trace of the A gamma square, which has on the main diagonal the several vertex degrees. A very important chapter in the theory of sign graphs is the chapter of, say, extremal problems. And many people study which are the, say, sign graphs with small spectral radius. Before telling the result, let me recall what is known in an unsigned context. Which are the graphs with small spectral radius? Well, the connected unsigned graphs with spectral radius not exceeding 2 were detected by Smith in 1970. And you see depicted here 5 graphs, and Smith proved that a connected graph whose spectral radius is 2 is one of the graphs depicted above. Now, we call these 5 graphs the Smith graphs. Smith also proved that a connected graph whose spectral radius is less than 2 is a proper subgraph of a Smith graph. If you see these graphs, you immediately realize that if a graph has a spectral radius which is less or equal than 2, it is a forest is acyclic, or at most is a cycle. The situation is quite a bit more complicated in when you study sign graphs with small spectral radius, since the connected sign graphs with spectral radius not exceeding 2 were detected by McKee and another Smith with Y this time in 2007. Look at these 3 graphs: the so-called toral tessellation with 2k vertices, this beautiful graph, sign graph with 14 vertices. Remember that the dashed lines represent negative edges, and this kind of signed hypercube with 16 vertices. Well, McKee and Smith proved that the unbalanced connected sign graph with spectral radius not exceeding 2 are switching equivalent to induced subgraph of this one of these 3 graphs. As you can see, many of them are neither trees or cycles. The identification of the connected sign graphs with small spectral radius were decisive to solve another kind of problem. For instance, if you are interested to find which unicyclic sign graphs among those of fixed order n bigger or equal than 4 have a minimal spectral radius, well, the results by McKee and Smith are very important, since you can just look at their unicyclic induced subgraphs. And this problem was solved in a paper by Francesco, Adriana Ciampella, and myself. And this is the guy who minimized the spectral radius. Well, let me say, this is a representative of the switching equivalent class graphs minimizing the spectral radius among all the unicyclic sign graphs of fixed order. As you can see, the two pendant paths on the right, on the left, has almost equal length. What does it mean? That it means that the lengths differ at most by 1. It is also we can also say that when n is even, we also have to consider the unbalanced cycles, since the unbalanced cycles when n is even are acospectral to this graph. This result is not surprising, since in a signed context we have not the asymptotical result recalled by Sebi yesterday, but as Francesco told us, the eigenvalues have a relationship with the difference between the closed walk of equivalent length, the positive closed walks, and the negative closed walks. And if you see this graph, it's obvious that the difference between positive and closed walks are, say, very small, say. You could also ask which are the minimizers for the index of unicyclic sign graphs. Remember that the index and the sign in the spectral radius is not the same, definitely is not the same concept when you study sign graphs. And not surprisingly, the minimizer of the index is not equal to the minimizer of the spectral radius. This problem was addressed by a beautiful paper by Akbari, Francesco Belardo, and others. And once again, you have here an unbalanced triangle. Look, there is just one negative edge here. And the three pendant paths have almost equal length. Once again, the length differ at most by 1. If you are interested to the unicyclic sign graph with maximal spectral radius or index, the situation is simpler, since the maximizers are the same for both the index and the spectral radius. The graph on the left maximizes the index and spectral radius in the class of all unicyclic sign graphs of given order. If you focus your attention instead only on unbalanced sign graph, you have just to take the same graph but the all negative signature. Similar problems were solved by looking at the maximizers and the minimizers of the spectral radius for the bicyclic graphs of a given order. And if you are interested to see them, please see our paper quoted before. But if you instead are interested to maximizers of the index of unbalanced signed bicyclic graphs with, say, n sufficiently large, you have not to go very far, since the paper has been published just 3 days ago in the latest issue of your Computational and Applied Mathematics, the SB journal, by this group of people from University of Shanghai. Now, this is the most embarrassing second of my talk, since when I started to prepare my slides, I was prepared to offer you this problem as an open problem. Unfortunately, well, I think that Zoran and myself found the solution just 2 days ago, and so. But I'm not superstitious, but I don't want to give you the answer, since I want to first write down the proof and check before advertise the result. But let me say that many people found very substantial partial results on this topic. Colin Stanic, Akbari, Gorbani, and a bunch of smart people from Iran. There is a gorgeous group of people working on sign graph in Iran. Very smart. My first last few seconds of this talk are devoted to the Laplacian matrix. This Laplacian matrix is positive semi-definite. It means that the eigenvalues are all non-negative, and the largest eigenvalue is obviously the Laplacian spectral radius. There are some connection with the signless Laplacian matrix. Francesco already told you about it. And this is important. The Laplacian spectral radius is bounded above by the signless Laplacian spectral radius. It means that all the upper bounds of this spectral radius are also upper bounds for the Laplacian spectral radius of your sign graph. For instance, the Laplacian spectral radius will be always less or equal than the sum of the two largest vertex degrees. There is also a up and lower bound. The Laplacian spectral radius is less or bigger or equal than the largest vertex degree plus 1. And this comes from the fact that G contains as a subgraph the star with delta 1 rays, and it holds the interlacing theorem quoted by Francesco a few minutes ago. Now, I know Francesco already told you about the geometric meaning of the least Laplacian eigenvalue, but it's an important theoretical fact since my first result in spectral graph theory concerned the least Laplacian eigenvalue. As Francesco told you before, if the multiplicity of the least Laplacian eigenvalue of G counts the number of connected components, the multiplicity of 0 for your sign graph counts the number of balanced connected components. And if gamma is connected, the least Laplacian eigenvalue estimates how far is gamma from being balanced. And, well, Francesco already told you about the frustration number. Here, the frustration number is 1, since for the graph on the left, since if you remove this vertex with degree 4, you obtain a balanced graph, whereas you need to delete 2 vertices on the graph on the right to get a balanced graph. And Francesco proved that the least Laplacian eigenvalue is bounded above by the frustration number, the equality holding if and only if, well, there are some structural conditions on his paper published on linear algebra application in 2014. This is really my last slide. Let me show you a graph, the spectral properties of a graph with 36 vertices. And I've computed for you the 4 spectral parameters that I defined along this talk. Here we have the index, here we have the spectral radius, here we have the Laplacian spectral radius, here we have the least Laplacian eigenvalue. The fact that it is 0, it suggests you that this graph will have at least one balanced component. And thankfully, this is my last word. Thank you.
Well, thank you, Maurizio. Since we caught up some time, I'll ask you to all the speakers to appear, and we have some time now to answer some of the questions that have been asked. Okay. So are the questions going to appear in the screen there? So whoever wants to answer the question, please do it. So the question appears, so it's not necessary to read.
Francesco, you don't have, you are muted.
Yeah, I have muted myself earlier. Okay, let me say that this is an open problem in the paper I mentioned earlier. So with -2, the theory works quite fine. So we expect that you can make the same arguments when you consider sign graphs. So you can extend the Hoffman theory to -3 and so on. So I would not say they are helpful. You see, you have more matrices, more sign graphs, you have more graphs to deal with. And then if you want to characterize these graphs with least eigenvalues in that interval, then you have to consider a wider family. and more possibilities.
Next question, please.
Oh yeah. I think I can provide an answer for this. As I know, I do not know results in this respect, but you see, when you think about ordinary unsigned graphs, you have blocks with the regular entries. So if you want a similar results with assigned graphs, you must have some regularity in these blocks connected the multipartite graphs. So if you have, say, homogeneous signs, perhaps you can, not perhaps, for sure you can write something. If you have some pattern on the edges, you claim that, okay, I have entries like this, you can. If it is completely random, I don't think so. So being a multipartite underlying graph, if you add some further restriction on the signs, perhaps yes.
If all the edges between two parts are of the same size,
next question,
then I believe that. Some results can be derived.
Yeah, but for sure, if you have the regularity, for sure you should have something.
Especially in the case of the Laplacian spectrum.
Yes, there is a paper, I think it was mentioned in the chat from 2018, perhaps there are even others. You see, the energy can be defined for sign graphs. For the adjacency, it's clear. For the Laplacian, you have several definitions. So you can consider the energy of sign graphs. But from technical viewpoint, this concept is, I would say, less important. As a curiosity, perhaps, yeah, can be considered and studied. There are some results, I believe, not too much developed. You see, even the theory of unsigned graphs is still not so well developed. So I expect that for signed graphs it can be even more difficult.
There are some results on that.
There are, yeah. At least I know 3 papers, published papers on this topic.
Perhaps more.
Perhaps more, yeah.
Okay, next question is there.
Yes, there is I think there is a very recent paper from Zaslavsky, some people from India, in which they consider this signed distance. I mentioned this signed distance as in signed diameter in the paper mentioned in open problems because this will restrict the number of distinct eigenvalues. So
there are few papers written by Zaslavsky and some people from India in which they have introduced the 2 types of distance matrices of signed graphs. They are very recent. All these papers published in the last 2 years. Or something like that.
I see.
Okay. Thanks for the questions. We'll stop now the questions. We hope we have some time afterwards. Francesco, may I ask you to introduce our next speaker, please?
Yeah, it's my pleasure to introduce the last speaker of this session, Professor Zoran Stanic from Belgrade, my good friend and I would say a real expert on spectral sign graphs. So Zoran, please, you will speak about this strongly regular sign graphs, which is a very interesting topic I have not covered in my talk.
Okay, thank you very much, Francesco. Just to check out, can you see now my slides? Let someone just say that everything is okay.
Yeah, we can see. Yeah.
Okay, then I can start. So I will talk about strongly regular signed graphs. This is a you will see natural generalization of strongly regular graphs. All results that you will see in my talk in the next, say, 20 minutes are defined and obtained in the last, say, 3 years. So I will start with a short introduction. Mainly, I choose to do this and in this way because I need to introduce some notation, introduce some definitions. Although you have already seen many of these things that appear in the first 2 or 3 slides here. So I will pass through all this very quickly. Given a graph G, something like this, we can define the signature on that graph, and then we get a sign graph. In my notation and in notation of all these slides, a sign graph is denoted by G with a dot. This interpunctual sign associates that we are is telling us that we are dealing with sign graphs, and when we remove a dot, then we are dealing with let me say unsigned or normal graphs. So we can manipulate between signed and not unsigned graphs by choosing to put a dot or to remove a dot. This is important in the spectral graph theory because every graph can be interpreted as a signed graph without negative edges, as I said here. So every G without a dot is also a signed graph, but with all edges being positive. Now, a signed graph is connected, regular, bipartite, and many other things if the same holds for its underlying graph. Okay. A signed graph is net regular if the difference, this will be important for the later, if the difference between positive and negative edges incident with the vertex is a constant on the vertex set. All right. And next, the adjacency matrix, already introduced by the previous speakers, is something like this. Yes. So it is obtained from the standard adjacency matrix of the underlying graph by reversing the sign of all ones which correspond to negative edges. Right? The corresponding eigenvalues are real and form the spectrum. The next thing is that we say that a signed graph is homogeneous if all its edges have the same sign. Okay, or if the set of edges is empty. And the next, a walk in a signed graph is said to be positive if the number of its negative edges is not odd. I can also say is even, but walk it may be that the walk doesn't have any edge. So zero. To consider it zero, it is better to say it's not odd. Otherwise, it is negative. And I will also use in my opinion, 2 basic concepts on defined sign graphs, both introduced by Francesco before me. So the concept of balance and the concept of switching equivalence. Switching equivalent signed graphs share the same spectrum. Switching equivalence is closely related to the switching isomorphism. Francesco already said the definition of both things. To see in a short table what we are talking about. Here is n is the order of graph of signed graph, and in the next row we have the total number of connected representatives of switching isomorphic classes with n vertices. For example, for n equal to 8, we have close to 5 million signed graphs. If we restrict ourselves to switching to the representatives of switching isomorphic classes, if we do not restrict ourselves to them, then we will have a much larger number. And to compare this with the number of unsigned graphs, we see that less than 1% of these close to the 5 million signed graphs are unsigned. So the set of signed graphs with n vertices for a fixed n is finite, of course, but there are many of them, which is good. All these graphs, signed graphs, can be found on this page. Next. I need to introduce something that Francesco already introduced, signed line graphs. So here is the definition. Francesco already defined them. So we define them by introducing this function defined on this Cartesian product, and each element is mapped into 0, 1, or -1. And this function is not unique, but each of them satisfies all these three conditions. And then we can define such a matrix, and signed line graph can be defined in several ways. The two of them are this one or this one. In the spectral theory, we frequently choose the later one. One of the reasons, there are reasons for yes and for no, and one of the reasons for yes to choose this approach is that spectral theory of unsigned graphs is naturally included in the spectral theory of unsigned graphs if we choose the second definition. Now, a signed graph is said to be exceptional if its spectrum is bounded from below by -2, but it is not a signed line. And now we are going to define strongly regular signed graphs, and here is the definition. We said that signed graph G is strongly regular. For short, it is an SRSG graph, an SRSG graph. Whenever it is irregular and satisfying the following conditions. First, it is neither homogeneous nor totally disconnected. We eliminated the two possibilities that are usually eliminated in the case of unsigned graphs. And then the three more conditions. There exists an integer such that this holds, where j square is an element of the square of the adjacency matrix. You have it defined here. And for all vertices joined by a positive edge. Similar thing for vertices joined by a negative edge, and similar thing for vertices that are not adjacent. Now, these parameters, the number of vertices, the vertex degree, and the remaining three parameters, A, B, and C, are called the parameters of an SRSG. Of course, it may occur that some of them is not unique. Say, if a G doesn't contain any positive edge, then A is arbitrary. But we can still call them parameters of strongly regular signed graph. Of course, similar parameters are defined in the case of unsigned graphs, and every unsigned graph can be considered as a special case of strongly regular. Every strongly regular unsigned graph can be considered as a special case of a strongly regular signed graph. In the matrix form, the previous definition can be given in this way. I believe that everyone can understand this definition. Now, next thing is this. We can compare the previous definition with Zaslavsky's definition, this one. And the signed graphs satisfying this definition are called by Zaslavsky very strongly regular signed graphs. Every strongly regular signed graph, every very strongly regular signed graph is a strongly regular signed graph. This is the second matrix equation tells us that each of them is net regular. I defined net regularity before. Now, an example with spectrum with this spectrum is given here. This sign graph is strongly regular, and it is also very strongly regular. Now, the next question: is there any relation between being a strongly regular sign graph and having a small number of eigenvalues? In general, no. But, for example, an inhomogeneous sign graph has 2 eigenvalues if and only if it is strongly regular with b equal to minus a. And if it is non-complete, then c must be equal to 0. A, b, and c are the parameters previously defined. For example, the case with 2 eigenvalues is considered in this way. The next thing, what is known about strongly regular sign graphs? In what follows, I will give you, let me say, the current state of knowledge about the strongly regular sign graphs. So, what is known? All disconnected SRSG are known. Here is a theorem. So, a disconnected inhomogeneous sign graph is strongly regular if and only if every component is an SRSG and SRSG with the same parameters. Now, also, we know all those that switch into homogeneous strongly regular sign graphs. Switching equivalence was defined before. So, a strongly regular graph G switches into an inhomogeneous strongly regular sign graph if and only if G is isomorphic to this one or this one, unsigned graph. These results are, let me say, simple. The next one is a characterization of bipartite strongly regular sign graphs. And here is the theorem. I will not read all this line by line. This theorem tells us that we can characterize all of them in terms of their eigenvalues and some, in the last case, in some block designs defined in the usual way. Every bipartite SRSG has 2, 3, or 4 distinct eigenvalues. The next thing is that we can consider those with 2 eigenvalues in more detail. For example, there are many results regarding them. First of all, we have the minimal polynomial. All right, and from the minimal polynomial, we can see that all of them are regular of degree is minus lambda times mu, where these 2 eigenvalues are lambda and mu. Right. The next thing is a relation with line systems, in which the lines are pairwise orthogonal or at fixed distance. If we denote that distance by phi, and if we set a rho to be equal to the cosine function of phi, then we get the corresponding Gram matrix that corresponds to that line system has the following form, something like this. All right, where A is the adjacency matrix of some sign graph. Now it is proved in some of the later references that we have something like this. All right, which is the relative bound for the number of our lines defined in the previous point, in the k-dimensional Euclidean space. It is relative because it depends on the other 2 parameters, the number of edges and this parameter rho defined previously. And there is a similar relative bound for that relates unsigned graphs. That bound is in a close relation with the number of lines in Euclidean space that are at the same distance with each other. And here, in the case of sign graphs, we have a bit complicated situation. They are orthogonal or at fixed distance. So we include another possibility for the distance between the lines. Now, this equality 3 is attained if and only if we have something like this. The first, the largest eigenvalue to be equal to the kth largest eigenvalue. In other words, if and only if the adjacency matrix of a signed graph has exactly two eigenvalues, these two eigenvalues. So the signed graphs with two eigenvalues are closely related to such sets of lines. Right? Next thing, what else is known? All regular signed graphs with vertex degree at most 4. This result can be deduced from the result of McKee and Smith. We already have seen this reference in the previous talk, and the result itself is given here. So all these signed graphs are determined, and to understand this theorem, only what I need is to define this thing here. This is a line graph of something here, and what is this? This is the cycle, the unsigned cycle, in which each edge is doubled by a negative edge. All right, and then take the signed line graph of that multigraph. Okay, and all of them are determined in this theorem. One of them is this one. Next, signed line graphs with two eigenvalues are also determined. Here is the result. Again, connected signed line graph has two eigenvalues if and only if it is switching isomorphic to one of these 4 possibilities for an unsigned graph, for a signed graph. So the first possibility is very simple. The next one is also very simple. This signed graph has 4 vertices, and the next 2 are the most important: the complete graph or a doubled signed graph, a doubled signed regular graph with n vertices. When a doubled signed graph is something which is defined in this way. So each positive edge is doubled by a negative edge. Now, what else is known? Spectra of exceptional signed graphs and maximal exceptional signed graphs. To introduce the result, I need to introduce the 3 graphs. So this M6 is represented by all the positive roots of the root system E6. M7 in the same way by the positive roots of E7, and similarly for M8. And now every exceptional signed graph with I eigenvalues greater than -2 is an induced subgraph of Mi. And these 3 graphs are given here. Some data on these 3 graphs are given here. Now, what else is known? All signed graphs with 2 eigenvalues and at most 10 vertices. This is a long list of signed graphs not given here. Bipartite signed graphs with 2 eigenvalues with 2 particular eigenvalues, plus and minus square root of 5, are in the characterization of non-bipartite ones. Again, I complicated the result. It will be not given here. The next. Now I will say some relations with other results. For example, for every R up to the switching isomorphism, there exists a unique R-dimensional signed cube with negative quadrangles. You have seen that cube in Mauricio's slides. Its eigenvalues are plus minus square root of R. And this result is used by Huang, who proved the sensitivity conjecture, a foundational problem in theoretical computer science formulated 30 years ago. This results has been published in Annals of Mathematics. So I believe this is this tells you about its significance. Now, we know the following upper bound. N is the number of vertices, and T is the codimension of an eigenvalue mu distinct from these 3 possibilities. So these results tells us how about the maximum multiplicity of an eigenvalue is in a signed graph when this eigenvalue doesn't belong to this set. Otherwise, the maximum multiplicity is not limited. This result is obtained in a joint work with my colleagues Farzani Ramezani from Iran and Peter Rawlinson from the UK. At this moment, I know exactly 2 signed graphs that attain this bound. This is again, in this case, 2-dimensional signed cube with negative quadrangles, and the previously mentioned M8 signed graphs with 120 vertices. Next, we can propose a kind of classification of SRSG to study them accordingly to some relations between their parameters. And here is such a classification, and some results regarding signed graphs belonging to strongly regular signed graphs belonging to these classes will be given in the next slides. I will not again read everything in details, but this classification is made with respect to the relations between the parameters A and B. For example, the first 2 classes have this equality in their definitions. Both, and the next 3 classes have the inequality between A and minus B, plus some other conditions, mainly related to the third parameter C. And the former matrix equations satisfied by any strongly regular signed graph, in the case of any of these classes, reduces to the corresponding matrix equation for that class. All right. And now, strong regular signed graphs that belongs to the first 2 classes are considered outside the context of the previous classification, and we know some things. We know that if G belongs to the first class, and if it is complete, then the adjacency matrix of the complement of its underlying graph is a 0 matrix. And therefore, we can conclude that G has exactly 2 eigenvalues. Here is another result for the signed graphs belonging to C1. If such a graph is non-complete and the complement of its underlying graph is connected, then G must be net regular. Next, if G satisfies the assumptions of the previous theorem, then it is the aforementioned very strongly regular signed graph defined by Zaslavsky. Next, if G belongs to the second class, then it has exactly 2 eigenvalues again. Strongly regular signed graphs of the third class are studied only in reference 4. You will see the list of references later. And what we know from that reference, we know the following things. Each of them is net regular, and all strongly regular signed graphs belonging to that class has some properties that are very closely related to the properties of strongly regular graphs, unsigned graphs. These properties are given in this theorem. So each of them has exactly 3 eigenvalues. One of them is the net degree, and the multiplicity of the net degree is 1. I believe that we all know that strongly regular unsigned graphs all have the 3 eigenvalues. If they are connected, then all have the 3 eigenvalues, and of course one of them is simple. In the theory of signed graphs, this doesn't need to occur, but if a signed graph belongs to this class, then we have something like this. Okay, there are many properties of complete strongly regular signed graphs of the same class, and many examples. And regarding the non-complete ones, I know only 2 examples. Both of them arise from the Johnson association scheme. And all of them have these 2 signed graphs have these parameters. So the first one has the 84 vertices, the second one has this number of vertices. Now, my colleague...
Could you please conclude, because we are overlapping the time of the next session.
I'm concluding. I'm concluding. Now Tamara and myself are working on the remaining two. And here are the references. I believe that all these slides will be available to anyone, so anyone can see all the references slowly and connect them with the previous slides. And this will be all from me. Thank you very much.
Well, thank you, Zoran. Thank you very much. Well,
we are very short in time, unfortunately. There is so much things to say about sine graphs, and unfortunately, we have to conclude. Perhaps we can answer quickly some questions, or we just stop and that's it.
I think I'll ask the organizers to give us a few minutes.
Good reference for spectral sine graphs? I don't think so. It's something that one should do. There are a few papers. I think perhaps my paper on lollipops is the oldest with sine graphs, but there is no, say, collections of results or
maybe
study
Francesco,
of enumeration.
Maybe it's not polite, but we have also the paper written with Alfredo and Matteo on generalizing the code seal and make a construction to build up.
Yeah, but it's a particular instance. If you think about a good reference for spectral sine graphs, I think, for example, the paper of Spencer and Hammers, in which you have enumeration and things like that. So we are missing something for sine graphs. So the table that Zoran provided earlier gives you already an indication about how this problem is difficult.
I have some paper.
Things are more complicated. You have more possibility, more things to study. Even strongly regular graphs are complicated to define in some sense. Any research?
Yes.
Yeah, please, Zoran.
Yes, I have some paper dealing with that, published a few years ago. All regular integral sine graphs with vertex degree at most 4, I think, no, at most 3, has been determined, and there are some particular results regarding those with 4, with vertex degree 4.
Yeah. It is also nice the fact that Vilmar were working on 2 different tables. Yes, it's a paper with us where we found some infinite family of integral sine graphs, and another paper with Braga and Rodriguez on integral unicyclic graph, non-unsigned. And well, just comparing the numbers of these integral graphs, we notice that you have just 15 integral graphs belonging to this family up to, say, order n, against 708, say, sine graphs. So it's obviously integral sine graphs are more spread since we have more possibilities.
Exactly. I don't know. I don't know. Zoran, perhaps you have some.
No. This could be related to the association schemes or strongly regular sine graphs at the first glance, but I don't know any results about this. It is an interesting topic, of course. It is possible that the answer to your question is yes.
Oh, I don't know.
No, I don't know.
Neither I.
Me too. Negative answer.
Further research is needed. Well, I think we should stop here and go to the other room, but I would like to thank everyone, and especially the speakers. I think this was a nice set of talks, and the idea to get to learn something about sine graphs, I think it was fulfilled completely. I thank you all, and see you in the next room.
Thank you very much for attending. See you guys.
Okay. Bye.